and they worship the devil. All right, go ahead. Sorry, I started your clock, but I can give you a pause there. So I started a little early. So you're going to be showing us what again?
Oh, so I don't have anything prepared. I was just going to talk about it real quick.
Please, about Airy's failure.
Yeah, so I linked the video in the private chat if you want to play it, so the audience can get the visuals. But it's pretty simple and straightforward.
Which one? The first one or second one?
The YouTube link is the Airy's failure. The second one is Parallax. If we have time to get to that, I'll type in negative Parallax.
Which one? It took me to Airy's failure search.
Oh, sorry, it's the Malcolm Bowden video. I meant to link. If you can link that, it's the first result.
Most famous failed experiment. Can't see because I've got a broken.
Yeah. I got you, bro. I got you.
I can find it. I just can't see.
The correct link is in the chat now.
All right, thank you. Okay, go ahead and start talking, and I'll play with no sound or play with sound.
Oh yeah, play it with no sound. I'll just talk over it near it.
Sounds good. Go ahead, have fun.
Okay, cool. So the premise here is that James Bradley, when he was doing stellar parallax observations, he had his telescope orientated 90 degrees. But what he found is that he actually had to get the star in the center of the telescope. He had to tilt it forward slightly. So they were like, okay, that's due to the Earth's motion, right? And that's where they got stellar aberration and all that kind of stuff from it, right? The extrapolation from it was that it was Earth's motion, and they even have a nice kinematic equation. Or, I'm sorry, they even have a nice ratio that they can derive to give them 30 kilometers a second when they apply that to the stellar aberration measurement. But that's a kinematic measurement, right? They can't tell you if the Earth is in motion or if the sky is in motion, and the starlight's just coming in at that angle already relative to your fixed position, right? So before Airy's failure, there was a guy named Arago, and what Arago did is he took his telescope and he half covered it with a prism, and he looked at starlight through the air through no blockage, right? And when he looked at it through the prism, he was trying to see if he needed to correct the telescope angle. Because when you introduce a medium, you're changing an independent variable in that situation. And the dependent variable, the correction, which would be the correction angle of the telescope, is going to be dependent on that. It's going to be dependent on the change in that. So if the prediction is, if you introduce a medium and you're looking at that same starlight, if the Earth is in motion, you're going to have to compensate for that velocity by tilting the telescope yourself, because the refraction index is going to take over that minuscule correction angle that you're making. If the starlight's already coming in at that degree and you're in a fixed position, then you won't need to make any corrections, right? The premise that the Earth is in motion was falsified right there, but you know how they are. They were like, what are we going to do? We'll just chalk this up as a null and keep going with our Copernican principle. And then Airy came along a couple years later and was like, hey, same premise. We don't know if based on the angle, if the Earth is in motion or if the sky is in motion. What'll happen if I fill this telescope with water? So natural observed phenomenon, observing the sky in motion, your hypothesis, trying to determine which is in motion. So you're going to introduce a medium to reduce the speed of light coming in. And based off of that relationship in the speed vector of Earth, you're going to have to move the telescope further, or it's going to stay in the same angle because it's already coming in at that angle. What happened, guys? Airy's failure. They say that there was a failure to detect the ether. So if you look at the heliocentric prediction in that paper from Airy's, the prediction was 30 arc seconds. So that's pretty big for their sky measurements, considering, right? So that's pretty noticeable. What they actually had to do was 0.08 arc seconds. They barely had to adjust it when he introduced water. The fact that it required a slight correction is all is proof that there's an ether drift. And the fact that it was off by so much for the heliocentric prediction, it's not even, motion isn't even on the table, dude. And then obviously from there you get into Michelson, Morley, et cetera. But yeah, I just wanted to give a quick rendition on that because it's the purest form of the scientific method that we all talk about, right? The old observation, define a problem, make a hypothesis, do an experiment with IVDVs, and derive your theory based on that. All of that was done, but the interpretation that we're given of it is skewed. So we really just we can stand on these old papers. We can stand on these arguments based on things in the sky, because when you introduce that independent variable, that's literally the deciding factor. That's how you tell the difference between kinematic measurement of, hey, we see this angle relationship when we ratio it with the speed of light at 30 kilometers a second. Is the Earth in orbit at 30 kilometers a second? When we introduce things and derive that relationship, no, it's not even close.
Right.
So the implication is that whatever is between us and the stars is moving and there's a drag that's creating the effects of it. So, so I'm not sure where I'm at on time or whatever. Do we have time to just start?
Let me see who
negative parallax or no?
Let me see here. Oh, I love negative parallax. My favorite.
Yeah.
We've got just pitch Lumen after you pitch. Give it 5 or a couple more minutes. We'll be with you after this one. Go ahead.
Okay, cool. So shout out to Sacred. He hit me up the other day or last Friday with a link to it was like a big link on negative parallax. So
Yeah, it's a Harvard paper, right?
So following up on some stuff that I sent him along with that, he found a link to what's been removed from the internet. So it's on archive.org. So if you want to add that link or put that out there, that would be dope. So you can read this.
That's that second one in the prime chat, right?
Yep. But basically this dude does an analysis of the what's it called? Psycho category log or whatever.
Okay.
And what that was is that was some stellar observations that they were doing. And they found that 47% of the data set, there's negative parallax. And then in the southern hemisphere, it's symmetrical, 47% on the other side as well. Dude.
Wow.
Like dude, that's so impossible on the globe. It's insane. And then it goes on from there to talk about the more modern ones. So they go over the Gaia 2 data set. That's a negative. That shows the same symmetrical relationship too. So don't ever let anyone tell you when they say, oh, flat earthers can't explain southern star trails and whatnot. Dude, negative parallax falsifies their model to an insane degree where they couldn't even explain, like you couldn't explain it on a stationary globe unless you would invoke the mechanism for that sort of thing. Like it's so bad for them. And the fact that it's symmetrical is crazy.
So tell me this just because I can understand a little bit. Maybe you can understand it better than me, but the more I think about this, I'm like, it's just impossible. So they tell us that GPS satellites are 22,000 miles away. And if I'm not mistaken, if you have a phone, then your phone calculates. So somehow the satellite would send a beam and it hits your phone. And your phone then does some calculation. How in the hell it would know when the beam left? I don't know. Supposedly we have some really accurate clocks somehow, but how is the phone accurate as well as the satellite? Okay.
So it's done on the one way they encode all the heavy accuracy part relevance of the information with the signal. So when they're sending those signals out, they're sending out the timestamp with it. So when your phone gets it, it doesn't have to do any crazy transformations or get any insane precision accuracy on its end. It's already encoded in it. So it just takes the difference off of that and it's accurate down to the millimeter off of that.
But if your phone is for it to know where you're at, then it needs to do some calculation of the time, and somehow the time would be dependent on where you're at, right? For instance, if let's say I'm standing on my street, or I'm standing on my roof, or I'm standing 2 blocks away, right? So in order for my phone to know where I'm standing, according to their GPS, the signal sent from the satellite with its time encoded would hit my phone. And because of the time that it took, my phone then knows where I'm at.
Yep. It's a time interval system.
Right. Exactly. So how would the atmosphere not be effective in slowing down that beam? So the beam is traveling.
Yeah, I got you.
Yeah.
Yeah. It's super negligible. They don't even account for it. Of all the factors they account for, that's not even one of them.
Okay. So think about what we're saying there. Then why would it be if I'm standing on my street and my house and 2 blocks away, how could that time that it takes to get to each of those spots not be negligible? You're standing right close to each other. How is the amount of time it takes the signal to get to me on the street or me on the roof or me on 2 blocks away? How would that be so vastly different that the whole thing doesn't make sense? I don't even think it works.
No, they break time down. This is what they say, that they break a second down to 9,192 millionths of a second. So it's like the time that it takes for C to propagate.
Okay, so how would it not make a difference? But how would it not make a difference then if there's clouds above me or rain or anything? If we're talking about 9 billionths of a second, then the clouds would slow down light enough that would cause it to think I'm somewhere that I'm not.
So going through air, the electromagnetic propagation, it goes through at 9.9 or 99.9999997 at C of C. So they don't even count for it.
So it refracts. So light only refracts none then in that case.
Yeah, essentially is what they're saying.
Even though it goes more and more atmosphere, so it would have to curve down, and it's like all that. Their stories are just so convoluted and garbage now at this point.
Yeah, so like the distances obviously are off, and then there's scale invariance with a shadow coordinate system. It can encode where it's at on the globe at 22 kilometers and give that differential and everything. So
Got
it'll
you.
tell you where you're at on the globe. So it's obviously way closer, and it's negligible through that. So I would
Yeah, I
say
think
that
it's closer to that.
it's just not that high.
Somebody asked me recently, I'm just going to ask you this. Are we positive that radio waves and light would travel in a vacuum?
Yeah, they do. And also,
But that's
we
been
do
tested to your
understand.
satisfaction, not just the words that they say?
Yeah, so there was a guy named, I forget his name, Demidov or Baranov, I forget which one did which, but one of them did interferometry in a vacuum, right? And what happens is you still get the pulsation, but the magnitude of the fringes reduces greatly. It goes down a ton, but you still get fringes and everything. It just reduces. It's pretty interesting. So imagine trying to, so when they do these vacuum tests, right? And they're like, oh, look, the speed of light's the same because it doesn't produce a fringe. What's actually happening is that you're trying to measure like imagine trying to measure the waves of the ocean, and you're like, okay, we'll do that. We've got to drain the ocean.
Right.
So the amplitude reduces down to where it's negligible, and they interpret that as C propagating at its full speed. Yeah, but what's actually happening is that they're reducing the impedance down, and that there's nothing to wave against to get that amplitude to the fringe.
I think the biggest thing is that
yeah, it absolutely does.
And the GPS satellites or the GPS code being closed source. And every time I say that, I see people in the chat saying, it's not closed source. Here's a link. Here's a link. Here's a link. No, I'm not saying that it's not a code that you can implement in your device. It is, but the transformations, the numbers, the mathematics is not for you to see. Yeah. So if you lived on a plane and you needed to return to somebody where they would be on the globe, what you would do is you would have those mathematics embedded in your balloons or whatever you're using, so that when a signal is sent from there and you are saying, here I am on the earth, they say, here you are on the globe. And that's it.
Bro, I did a presentation on that recently. That's exactly how it would work. So when I said, I mentioned earlier, like a shadow coordinate system, that's exactly how it would work. It would all be relative to the center of the ECI. So you would take like the center of the North Pole, right? You would have everything out from there. You would have its accurate position and everything in real space relative to the actual map of everything. And then you would have that projected onto a globe, right? And the difference in there would all be encoded in, and you would just do your scale invariance. So when people see a satellite move across the sky at whatever speed they say, they're like, oh yeah, it's proportional to it going across the speed at that distance, but the altitude could be vastly different. But the signal that they send is it's encoded with the information that the satellite is coming from 22 kilometers out, right? So it's already backwards compatible with it on the back end. And in addition to that, you would already have it work that way, and not even necessarily for nefarious purposes, for military reasons, right? Because you wouldn't want to have somebody, of course, be able to actually derive the altitude of your satellite so they could attack it or something like that, right? Its actual position. So you would have it, that would already be built into it. And then on top of that, I don't know if you noticed, Jaron, but they have what's called meridian corrections built into the signal time. So it deduces like how long the time was taken, and then applies a meridian correction. So it's basically like how long the speed of light if it propagated for X amount of time, how many meridians would it have crossed, and they adjust the time of that, thereby or thus adjusting the distance. So like you can't even use GPS to get an accurate reading over long distances, because it's always going to go back to the globe, but it's going to be super accurate short distances. But that's how they're going to hide it.
Correct.
True. When you try and check over long distances, it's going to be globular.
Yeah. These guys are like, show me a plane that's going 1,200 miles per hour. I can't, because you believe in the GPS distances.
Dude, yeah, it gets super hard with that because it's already corrected and baked in. Like I was reading this paper from the 90s where these gentlemen wanted to go and look at GPS corrections to verify the speed of light is the same in all directions. So when they did their analysis from the raw GPS data from the main central place in Colorado where they store all the data, the data that they got was already SAGNet corrected, doing air quotes. I'm sorry, my green screen is blocking it out, but it was already quote unquote SAGNet corrected. And they say that this is due to the rotation of the earth and whatnot.
It doesn't make any sense.
Not to get into the full specifics of that. That's absolutely not the case. And what they're actually doing in that data is applying first order velocity corrections to the speed of light to make it seem like on the GPS end that the speed of light is the same and it's deriving the distance based off of that constancy. That's not true. They already corrected it on the back end before anyone even gets to see it. So the idea that like you can just go to an open source, dude, I want to go to GitHub and debunk the globe.
Dude. Jesus.
Yeah, miss me with that. You know what I'm saying?
No, and then a guy that we had the interview with, Austin and I were talking to him, and he's like, yeah, but it works. It's like, Yeah, it works. That's the deception. Like you shouldn't be surprised if we're saying, hey, you're being deceived. And then you're like, yeah, but it works. Yeah, we know that. That's why it's a deception. If it didn't work, we wouldn't be having this conversation. Nobody would ever have believed it.
It works. It works off classical mechanics, and they retrofitted relativity on the back end of it starting in the 90s, in the mid 90s. There's a paper about it where an engineer had to come out and go, all right, we're not accounting for, people have been asking why we're not accounting for relativistic corrections. So basically what's happening is the sensitivity of our equipment is such that we don't need to account for special and general relativity because the velocity corrections and the gravitational potential corrections are canceling each other out. So we can just use classical mechanics. And then after that, they started back ending relativistic transformations and all that to explain everything. And it's cool, man. GPS only works because of relativity. It's built on the back of the classical mechanics.
Well, keep doing what you're doing. Keep putting out what you're doing because it's helping a lot of people. It's helping me understand things clearer. You can explain things a lot simpler than I can find them on phys.org or something. And it just helps me to watch every. Sometimes I do have to watch them more than once, which I'm not a huge fan of, but I do what I have to do. But I appreciate it.
Yeah.
It really helped out a lot. Anything else for you?
No, that's it, man. So check us out. Friday, we got Flat Earth Friday. We'll be streaming that for a little bit. And on Tuesday, we'll be doing a LIGO presentation at 7 p.m. Toby and I will be presenting on that and the fraudulence of LIGO. We'll be going in depth on that.
Oh, Brenda heard that.
And then on Thursday, we'll be doing probably reading something. We'll be doing some live research and doing some live reading stuff.
Lovely. And what time does Flat Earth Friday start?
Usually 8 to 9 p.m. It fluctuates a little bit, but that's generally
Eastern or?
Yeah.
Okay.
Yeah. And they go super late too. So if you want to pop through or whatever to come on by, they always shout you out and give you a shout out to the boys, the level heads.
Yeah, level heads shout out. Okay, I'll head over there. Appreciate it.
All right. Peace, bro.
Let's go to Pitt.